Welcome. Yes. Okay. So today we have Gonçalo. He's a second year PhD student, uh, supervised by Bruno Martins and Krisa. And he's going to present us about evaluation metrics for vision language model. Thank you, Gonçalo. The floor is yours.
Thank you.
Yes.
So first, I want to thank Priberam for this opportunity and for all of you attending. As Gonçalo said, I'm a second year PhD student here in Technical. And today, the presentation will be regarding all the research that I developed on my first year of PhD, which with the focus of improving evaluation metrics for vision language models. I don't know why this is. Oh, yeah. You see? Maybe I'll move it. Yeah. So, as an introduction, the evaluation of vision of image captioning has become an important topic of research in order to assess the quality of these new vision language models. But conventionally, this assessment has relied a lot on human references. So captions that were written by humans and that they are compared then against these machine-generated captions. And so the dependency of the availability of this extra information and the fact that conventionally by using these human references to evaluate, the evaluation as was done mainly on the text domain. And this is there's a high contrast with the reference wheel way, which we humans evaluate and assess the quality of captions. So this led to the development of more sophisticated methods, such as CLIPScore. CLIPScore is essentially a modified cosine similarity between the embeddings of both modalities, of the vision and the text produced by a clip type model. This type of models are dual encoders that were previously pre-trained in a contrastive way. So the objective here was to align both the embeddings regarding similar objects. But despite the advancements on the field and the relatively high correlation that this type of metrics seem to have with human judgment, there are still a lot of challenges to overcome. And one in particular is the low inclusivity, since despite these recent advancements, the research has been done in its majority to center in English and Western cultural research. So multilingual captioning evaluation has remained relatively unexplored. Another thing is that there's low interpretability of these evaluation assessments, and in many cases, the goal and an effective evaluation is not only an overall score or an overall quality estimation between the caption and the image. So sometimes it's much more important and valuable to really detect and have a granular assessment of the words in the caption and which parts of the caption positively or negatively impact the overall score at the end. And finally, another challenges that this type of metrics are facing is low reliability. Since existing image captionings provide only a single point estimate. So without incorporating any uncertainty or confidence estimation of these scores, sometimes makes these metrics really hard to deploy in real world applications. So this presentation will be divided in 3 parts, and the first section will be regarding improving in captioning evaluation, and the results for this first section are regarding a recently accepted paper in findings of NACO. And the contribution motivations for this paper is essentially this was to increase multilingual resources in image captioning evaluation. And we do this firstly by using a machine translated scheme with a quality estimator model to create a cost-effective solution to extend existing and well-established benchmarks to multiple languages. Additionally, we also repurpose natively multilingual datasets for evaluation of semantic and reasoning capabilities of vision language models. And then we use this data, this multilingual data, to further explore the use and effectiveness of CLIPScore in these multilingual scenarios. So we use these multilingual benchmarks for further fine-tuning and assess image captioning evaluation models. So to start, the machine translated scheme that we proposed was for each instance of each English benchmark, we sampled for each instance 25 translations using an open source model. And then with the quality estimator that we use, which was Comet Kiwi, we selected the highest scoring one. So for each instance, we did 25 translations and select the best one. And we keep doing this for all for both the target benchmarks, Vickr and VALS, which are existing well-established benchmarks on the field that I will further detail more what these benchmarks trying to assess. And we target 9 different languages. And in total, we achieved more than 200,000 multilingual instances worth of data. And with this data, we further fine-tune a CLIP model using the machine-translated Vickr data set, the training set of this data, and a natively multilingual data set called Cross Model 3600. And we propose a fine-tuning scheme where we use 2 types of losses and combine the gradients from those provided by those losses. And we use contrastive loss using both the machine-translated Vickr and the cross model, the natively multilingual data set, to enhance model ability to process multilingual and multicultural instances. And then we use also Pearson loss with the machine-translated Vickr. We use, in this time, when using this second loss, we use only the machine-translated Vickr because this loss tries to align the CLIPScore values with the human judgment, and we needed access to these human judgments. So, and the machine-translated Vickr, from the two, was the only one that we had access to this type of information. So the 2 terms in the contrastive loss. So the 2 terms in the contrastive loss, they are like in the SIJ, they are so when we compare both the textual embeddings and the image embeddings, we produce a matrix. And one term is regarding the multiplication of the term from the image to the caption, to the image to the text, and the other the text to the image. Exactly. So now for the after this we had to choose a CLIP model to be fine-tuned using that fine-tuning strategy, and we compared a lot of already multilingual variants of CLIP against a bunch of CLIP English-centric CLIP versions, and in this first test we wanted to compare the performance of these multilingual models in English-centric data, because we wanted to test if the by exposing the model to multilingual data if we had a negative impact on English performance. So in this graph here, in this plot, what we are seeing is that we picked the best performing model, multilingual model that we tested, and the best English model that we performing that we tested, and we compare both of them, and we can see that they have similar. They are similar in the terms of size. They both are models of 1 billion parameters, and they were both trained with 5 billion instances. But the multilingual model was only trained with 2 billion instances worth of data, of English data. But despite having trained with less than half of the amount of English data, it performed very comparable to the best English model. And there's a key takeaway here, which is the multilingual model could generalize across languages while excelling in comparable results on English performance. So we selected this model to be, and we further fine-tuned it with the fine-tuning scheme, and then we further test the performance of this model on the machine translated benchmarks. So Vicar, as I mentioned, is a benchmark for testing human correlation with human judgments. So on the left side of these slides is the results before and after fine-tuning of this model, and this is Kendall Tau. It's because what we want to test is the correlation of this of the CLIPScore values produced by this CLIP model with the human judgments. And VALS is a benchmark for distinguish real captions from misaligned ones. So it's an accuracy test, and the objective here is to distinguish the real captions from captions with containing some type of error. And we can see that after fine-tuning, we have a consistent improving in performance across both benchmarks and across the evaluated languages. In addition, we also tested the performance of our fine-tuning model on natively multilingual data. So what we did was to repurpose existing natively multilingual data sets, XVNLI and Marvel, to test and construct an evaluation task for evaluating these vision language models. So for the XVNLI tasks, they rely on identifying entailment, neutral, and contradiction captions. Both the three tasks, the objective is the same, but they are increasing in difficulty. But the objective is the same, is identifying entailment, neutral, and contradiction captions with respect to an image. And in Marvel, the objective is to, given a pair of images and a caption, identify if the caption corresponds to both images or not. And after fine-tuning, we also see this incremental increase in performance across the tasks of both benchmarks. So as a recap of this study, the study highlights the importance of having and benefits of having multilingual research in image captioning contexts. Our findings show that multilingual models perform just as well in English while excelling in multilingual tasks, turning these multilingual models a much more valuable asset. We proposed a cost-effective way to extend existing benchmarks without compromising the quality of the original benchmark, aiding in fine-tuning and evaluation. And we proposed a fine-tuning scheme that enhances performance of these multilingual models across different data sets and tasks. So I'll take a break here to just drink a little bit of water. As a second part of this presentation, as you might expect by the motivation, will be regarding interpretability in image captioning. So the results here will be they will be regarding a paper that is currently under revision at IRR. And the idea is to extend these CLIPScore-like metrics. Note that these metrics are single point estimates, and to extend this type of metrics in a more granular assessment of each word. So the idea is to, given an image and a caption, try to see which parts of the caption contains an error and are negatively influencing the overall score at the end. So as you see in this example, the word carrot is clearly an object that it's not on the image, and it's a wrong word. So the objective in this part of the presentation is exactly this: is to try identifying the wrong words in the caption. And to do this, we need to have a way to map the single point estimates to a granular assessment. And the way we did this was to, okay, so if we mask parts of the input, especially the more relevant ones, we can see that this masking will affect the overall score at the end. So in this example, if we mask the word carrot, since it's an object that it's not contained in the image, it's very likely that the overall score at the end will increase compared to the original one. And if we do the same on the word shrimp, which is a word that it's on the image, it's very likely that if we mask this word and compute the CLIPScore, it's very likely that the CLIPScore at the end will be lower than the original one. So if we repeat this process by randomly masking parts of the inputs and accumulating its difference, we can already kind of have a naive classifier where each word we can associate a score, and the higher the score, the more likely it is that this word is wrong, is negatively influencing the overall score. But there's, as I said, only doing this, it's very naive, because in cases, if we assume always the wrong word as being the highest one in this type of strategy, we would end up in cases where we contain no errors. We would end up in cases of having a lot of false positives. And in cases where we have multiple inadequate words, we end up having a lot of false negatives. So the problem here is where and how do we cross this threshold? So how do we select a lambda that are helping us to construct a prediction set in a meaningful way? And the way that we do this is by using conformal risk control. So the idea is to select this lambda in a calibration set in a meaningful way. So we need to have to define a risk, which is our preferred quality criteria, for example, false positive rate or false negative rate. And the idea is that to select a lambda, which the probability of the risk being below a certain tolerance level that we define is achieved with high confidence. And it's an important thing to take in mind is that we assume that this calibration and test sets are samples from an unknown underlying distribution. So this could lead to differences in data between these two sets, and this could reflect in violations of our goal and the chosen risk tolerance thresholds on the test set. So the solution here is to take this drift, take these deviations into consideration when constructing this conformal risk control method. And the idea is that we have the risk that we define, and then we we overestimate this risk. So we construct an upper bound of this risk, and we target this upper bound. We target this overestimation. So the idea here is that we assume that they are the calibration test sets, they are different in some way. We don't know what these differences are. We just know that they will have slight deviations between each other. And we construct this overestimation of the risk in order to be more conservative and indirectly account for these eventual data drifts. And then after having this overestimation of the risk, we select the lambda such that the confidence region to the right falls below the target risk tolerance. And one thing that it's important to take here into consideration is that by selecting lambda as such that the confidence region to the right falls below the target risk, this function needs to be monotonic decreasing. So it's an important property of the function, of the risk function, to use this type of strategy. But let's not drift from our main goal here. Remember that in this case, our main goal is to detect and try to identify the wrong words in the caption. So the risk control part is just a calibration set. It's just a calibration way to define the threshold to construct the prediction set. So we mask parts of the sample, of the caption, and of the inputs. We assign a score for each word. Then we calibrate using conformal risk control the threshold, and we use this threshold to construct our predictions. So in this type of scenario, we could have two different types of benchmark. One, which are the fault type benchmarks, which they can be seen as a multi-class word detection, where at maximum we have one error on the caption. Or we can have the rich HF, which is a multi-label word detection dataset benchmark, which we can have multiple wrong words in the caption. And for the fault type benchmarks, the risk that we define is false discovery rate. We target 20%, and in here what we are seeing here is that we target 20% in the calibration, and that then we test if the risk was controlled to the desired level on the test sets. And we do the same for the rich HF, but in this time we used false positive rates, and we target 30%. Now, after the calibration process of our method, remember that our method is masking parts of the inputs and calibrating the threshold without doing any fine-tuning to this process. We are just grabbing a pre-trained model and use the CLIPScore we mask by masking parts of the input and calibrating the threshold to construct the prediction set. There's no fine-tuning here. Nonetheless, we could achieve better results when compared, for example, with ALOA in all the evaluated benchmarks, both multi-class and multilingual. And this ALOA actually leverage large language models to do this type of assessment. So just by having our simple strategy well calibrated, we were able to achieve very comparable results with the state of the art. And one important thing also to take into consideration is that this approach of calibration is model agnostic. So it's a complementary strategy that could be used also in existing approaches. So here are some qualitative analysis of both tasks. So there's a color code here. There's the words in green are true positives. So, but this means that it's a wrong word in the caption that our model correctly identified it. There's the yellow ones, which are false negatives, which is a word that was wrong and our model not identified it, and false positives, which is a word that it's that our model decided to assign it as being wrong, but they in fact they are not. I'll have a break here. So in the third section here of the presentation, as you might expect, it's will be a talk about reliability in captioning evaluation. And yeah, it's the same paper as the previous one, but I decided to, since they are two different subjects, I decided to have a different section for both of them. And the idea here is extend the CLIPScore-like metric to include a confidence estimation for each image captioning quality assessment. So in here, remember the CLIPScore is a single point estimate without any uncertainty or confidence estimation associated to this prediction. And the idea here is to extend this to have a kind of distribution where the average of this distribution can be seen as the prediction. And we can use the standard deviation, for example, as an uncertainty estimation of this prediction. And if we recap the way that the same strategy that we used to do the granular assessment by masking parts of the input, we can already by doing this, we can already have a type of raw qualitative raw distribution of scores that they could be used to help quantify the model uncertainty. But we also want, in a similar way of the previous framework, is we want to calibrate these distributions in a way that are meaningful, that this distribution want to further calibrate them to mean something. And a way that we started this, so to do this, we need to find some variable to be calibrated. In the previous section, it was the threshold, and in this section, it will be a scaling factor of the standard deviation of these raw distributions. And the idea here was to fit a truncated Gaussian and use the mean of the empirical mean of these raw distributions and the standard deviation scaled in a factor of lambda. And by doing this, after fitting, we end up with a truncated Gaussian where the mean, both mean and standard deviation of this after fitting the truncated Gaussian to be affected by this lambda this lambda. Why? Because the standard deviation is expected to be modified, but the reason why the resulting mean is also affected is because we are using truncated Gaussian, so we do not allow the tail parts of the distribution to extend in the same amount. So what this means is that the distribution gets flattened and converts to a uniform distribution as lambda increases. And the idea here is to calibrate this lambda, this calibration variable, with the same principle. The idea is to define a risk, which is a preferred quality criteria, and we calibrate this lambda factor, the scaling factor, in a way that the probability of the risk being below a certain user-defined threshold with high confidence. And the risk that we define in here is this one. So it's 1 minus the value of UPS. UPS is a standard metric in uncertainty awareness domain, and it's essentially the correlation. The little r here is Pearson correlation, and UPS is the correlation between our uncertainty estimator, which in this case is the standard deviation, and the prediction error. So the idea here is to calibrate to a low user-defined tolerance of our risk. And by doing this, we are targeting an increased correlation between our uncertainty estimation, which is the standard deviation, and the prediction error. But here it's a challenge. So in this case, we can no longer assume that this risk is monotonic decreasing. So we cannot use the same framework that we previously used to find this lambda in order to have the region of the risk at the right of this lambda being below our defined or using defined tolerance. So the solution here was to use another technique called learn and test technique. And the idea of this strategy is, so first define the risk, which we already did. Then we define the tolerance level, which in this case, since our objective is to increase the original UPS, is the same of setting the lambda to 1 in this risk function. And then we define a set of lambda values. And for each lambda, we associate an hypothesis test where R is higher than our tolerance level. And the idea here is to assemble to gather all the lambda values where we reject the null hypothesis. And by rejecting this, we are we achieve our objective, which is finding a lambda that holds the validity of our inequality. And this is what we did here on this plot. On the left side is the risk. We can see that it's not monotonic decreasing; it's a convex function. And on the right, associated to each lambda, it's the p-values. It's the p-values associated to each lambda. So, and the idea is to select all the lambdas where the significance level, which is the line on the green line, fall below this significance level. And in this particular case, we wanted to select a lambda that achieved the highest UPS. This is the same as selecting the lambda with the lowest p-value, and it was what we did. Finally, we compare the performance before and after this calibration process, and we compared this on UPS across 4 different benchmarks. And on the remember that by calibrating this lambda, we besides affecting the standard deviation, we are also affecting the mean. So this improve in UPS could lead to a degradation of correlation with human judgments, which is something that we do not want. So we needed to, on the right side, also test this correlation with human judgments to see if, even though we increase in UPS, we didn't degrade too much on. So the calibration set was on the validation part of Vicker. So Vicker has training set, validation, and test set, and we calibrated this model, this system on the validation part of Vicker, and now we are testing on different test sets with the same objective. So which they are all benchmarks for testing human correlation, and we can test this UPS, which is our preferred criteria. And by looking at both plots, we can see that we achieved a significant improvement in terms of UPS across the data sets without significantly compromising correlation with human judgment, which is what we wanted. So as a recap of this paper, it englobes both the second and third part of this presentation. And this study highlights the importance of fine-grained caption assessment and confidence estimations. We showed competitive performance against more complex models on several well-established benchmarks, while all allowing more controllable and trustworthy performance in detecting word errors. And we also showed improvement in correlation between the uncertainty estimation and the prediction error without compromising human rating alignments. So I finished my presentation. Thank you all.
So can you motivate why you use the truncated Gaussian?
So
I know you cannot use a Gaussian, but
yeah, this is an approximation, but the reason why we couldn't use a Gaussian in this case was
because it's between 0 and 1.
Yeah,
but
first of all,
why the truncated Gaussian, not some distribution that is native to the 0-1 interval, the betas?
Okay, so I wanted since we wanted to calibrate, I already knew that I wanted to calibrate for UPS. So I wanted to something that by moving a specific calibrated factor, for example, lambda, I wanted to both change both mean and standard deviation of this for UPS, and because if I calibrated to only the scaling factor of the standard deviation, and if it didn't affect this mean, like I would increase all the intervals of all the distributions in the same way, and this would end up not having. I'm not explaining this correctly. So
it's hard to explain in words.
Like it's hard to explain. So I didn't want to have the same. So I want to allow both mean and standard deviations to be affected by the same factor, because this would help me in terms of trying to calibrate to this specific criteria, because I believe, like, if for better distributions, like it's hard to explain.
Don't worry. We can talk offline.
Okay, but I believe that there could definitely have this other distribution that could be used to do this. To use to calibrate this, but yeah.
Okay. Any other questions? No. Are there any these types of works about evaluation, not only but for multimodal models for image and text, but for also like audio, image?
Okay.
Completely multimodal. Yes.
Completely multimodal. I'm not sure, but I think, but maybe a similar thing I believe for audio, for example, it's something hard because I think audio needs to like, for example, this type of CLIPScore are based on a transformer model, and since they move like the complexity move quadratically with the length of the input, maybe I think audio is faces a little bit of difficulty on since the inputs on audio are much longer than captions or images. Even images, they are fitted most of the cases to 225 resolution. So
yeah,
yeah, but I don't I'm not sure if there exists something similar to this type of quality estimations for audio. But it's at least for image for the multimodality of image and text, it's what has been used to validate them.
thank you. Any other questions? Okay, I think that's it. Let's give another round of applause. Thank you.